66 million years ago, an asteroid struck Earth and disrupted nearly every ecosystem on the planet. On land, the collapse is familiar. Dinosaurs disappear, forests burn, and the sky darkens for years. But the ocean held most of Earth's living space, and its story followed a different path. Entire marine systems failed in a geological instant. Plankton populations fell sharply, removing the base of the food web. Predators continued for a short time, then began to decline as their food sources disappeared. The ocean did not empty, it lost structure. For millions of years before the impact, marine life had remained stable. Food chains held their shape, and large predators dominated with consistency. That balance did not return. Some environments became sparse in ways not seen before. Large familiar forms of life were suddenly absent. What remained was uneven, fragmented, and still changing. Recovery did not begin with dominance. It began with survival. Small organisms, deep water communities, and adaptable species persisted where others could not. They did not restore what was lost. They began building something else. Over time, entirely new ecosystems formed from these survivors. The ocean that emerged no longer resembled the one that came before. In tonight's story, we follow how the ocean changed after the dinosaurs died, and how new life emerged from collapse. Before we dive into tonight's story, I'm always curious how a science story like this fits into your day. Do you listen while settling in to rest, or while moving through something like work or study? Let me know in the comments. Now, we follow how the ocean slowly rebuilt into a different world. Long before the moment of disruption, the ocean moved in a rhythm that had endured for millions of years, a steady pulse shaped by warmth and depth. Sea levels stood high, spreading water far across the continents, softening the boundaries between land and sea. Vast inland seas settled over low regions, turning what would one day be dry ground into shallow, sunlit expanses where marine life drifted and fed. Coastlines were not fixed lines, but shifting gradients where waves reached deep into the heart of continents and lingered there. In these broad, warm waters, life arranged itself into patterns that held with quiet consistency. Sunlight filtered easily through the shallows, feeding immense populations of microscopic plankton. These tiny organisms, suspended in the upper layers, formed a living veil that stretched across entire ocean basins. Their presence was subtle, almost invisible, yet they sustained nearly everything that followed above and below. Beneath this drifting foundation, chains of life extended upward in measured balance. Small fish and invertebrates grazed on the plankton, moving in slow, coordinated currents. Larger predators followed predictable paths, rarely straying far from the abundance that supported them. Energy passed smoothly from one level to the next, without sudden breaks or shortages. The structure of the ocean was not rigid, but it was dependable, shaped by repetition and time. Across these waters, ancient reptiles moved with quiet authority. Mosasaurs glided through open seas, their long bodies bending in steady motion, while plesiosaurs traced slower arcs near the surface and along continental shelves. They were not isolated figures, but part of a system that had settled into place long before, each species occupying a role refined through countless generations. Their presence did not disrupt the balance, it completed it. Among them, ammonites drifted and pulsed, their coiled shells catching the light as they moved through the water column. They existed in vast numbers, forming an essential link between the smallest producers and the largest hunters. Their life cycles followed rhythms tied to the seasons of the sea, rising and falling in patterns that had repeated so often they seemed almost permanent. The ocean itself reflected this stability in its chemistry and motion. Temperatures remained warm across much of the globe, reducing sharp contrasts between regions. Currents flowed in broad, gentle circuits, distributing heat and nutrients without sudden interruption. Even in deeper waters, where light no longer reached, conditions shifted slowly, allowing life to adapt without urgency. Reefs and shallow marine habitats flourished in this environment, building complex structures that hosted countless forms of life. Each layer of the ecosystem supported another, creating a depth of interaction that extended from the smallest organism to the largest predator. Nothing stood apart, and nothing existed without connection to something else. Time, in this ocean, felt expansive. Generations passed without altering the fundamental structure of the system. Evolution continued, but it moved gradually, refining rather than replacing. The forms of life that dominated these waters did so not through sudden change, but through long periods of quiet persistence. There were no signs within the ocean itself that this balance could shift so completely. The surface shimmered with the same patterns it always had, and the depths remained calm, holding their slow, steady processes. Every movement, from the drifting plankton to the passing shadow of a reptile, belonged to a world that seemed fully formed. In this ancient ocean, life did not struggle to define itself. It existed within a structure that had already been shaped, already been tested, and already been sustained across immense spans of time. At first, it arrives not as a sound, nor as a visible presence across the ocean, but as a sudden, overwhelming release of energy concentrated at a single point on the planet's surface. In the region that would one day be known as the Yucatan, an object from beyond Earth meets the crust with a force that compresses rock, water, and air in an instant, converting motion into heat and pressure beyond ordinary scale. The ocean nearest the impact site does not have time to respond in any gradual way. Water is displaced violently outward, forced upward and away, as the seafloor itself shifts beneath it. A cavity opens where the surface once lay, exposing deeper layers for a brief, unstable moment before everything begins to collapse back inward. The boundary between sea and sky blurs, replaced by a rising column of vaporized material and superheated debris. From this center, shock waves move outward in all directions. Through the atmosphere, they travel as expanding fronts of compressed air, while beneath the surface, pressure waves propagate through the water and along the ocean floor. These waves do not resemble familiar currents or tides. They carry immense force, passing through entire basins with a speed that leaves no region untouched. As the energy spreads, the surface waters across distant parts of the ocean begin to react. A thermal pulse generated by the impact and the material ejected into the upper atmosphere returns downward as radiant heat. For a brief period, the upper layers of the ocean absorb this influx, causing temperatures to rise rapidly. The change is not uniform, but it is widespread enough to alter conditions across vast areas. Near coastlines, the movement of water takes on a different form. The initial displacement grows into waves of extraordinary scale, driven by both the collapse of the impact cavity and the shifting of the seafloor. These waves move outward, gathering height as they cross open water, then transforming again as they encounter continental margins. When they reach shallower regions, their energy compresses into rising walls of water that move inland with sustained force. Shorelines that had remained stable for long periods are reshaped in a matter of hours. Sediments are lifted, carried, and redeposited in new patterns. Marine environments extend briefly across land, then withdraw, leaving behind layers that record the passage of this movement. In some regions, multiple waves follow one another, each altering the terrain further. Beneath the surface, the effects continue to unfold. The pressure changes associated with the passing waves disturb sediments along the seafloor, lifting fine particles into the water column. This suspended material spreads gradually, altering clarity and light penetration in ways that persist beyond the immediate event. Chemical conditions begin to shift as well, influenced by the influx of material from both land and atmosphere. Even in regions far removed from the point of impact, the ocean does not remain isolated from these changes. The interconnected nature of its basins allows energy to move across distances that would otherwise seem too great for a single event to influence. Each part of the system receives a portion of the disturbance, though the intensity varies with distance and depth. What had once been a system defined by continuity now absorbs a sudden interruption. The patterns that governed movement, temperature, and interaction are altered within a span of time that, in geological terms, is nearly instantaneous. The ocean continues to move, but its motions now carry the imprint of an event that has reached into every layer, from surface to depth, and from coast to open sea. Light fades in a way the ocean has never known, not as the gentle shift between day and night, but as a dimming that does not lift. Particles lifted high into the atmosphere begin to spread across the globe, forming a suspended veil that filters the sun before it can reach the surface. What arrives at the water is no longer full illumination, but a weakened glow, diffused and uncertain, unable to penetrate as it once did. At the boundary where air meets sea, this change settles quietly at first. The surface still moves with familiar patterns, but the energy that once passed freely into the upper layers begins to diminish. Sunlight, which had sustained vast populations of microscopic life, now struggles to reach even shallow depths. The upper ocean grows dim, its clarity altered by the absence of direct light and the gradual accumulation of fine particles drifting down from above. Within this dimmed layer, photosynthesis begins to falter. Phytoplankton, which depend on light to convert carbon dioxide into organic matter, find themselves in an environment that no longer supports their continuous growth. Their processes slow, then stall in many regions, as the energy required to sustain them becomes scarce. These organisms do not disappear all at once, but their numbers begin to decline with steady persistence. The reduction spreads unevenly across the ocean's surface. Areas that once supported dense blooms of microscopic life become sparse, their productivity reduced to a fraction of what it had been. The living film that had stretched across the upper waters thins, leaving larger gaps between populations. In these spaces, the flow of energy into the system weakens, altering the balance that had long defined marine life. As phytoplankton decline, the immediate effects ripple outward. Organisms that depend on them for food encounter a diminishing resource, and their own activity begins to shift in response. Feeding patterns change. Movements become less predictable, and survival becomes tied to increasingly limited patches of productivity. The structure of the upper ocean begins to loosen, no longer anchored by the steady presence of its primary producers. At the same time, the reduction in sunlight influences the temperature of the surface waters. Without consistent solar input, heat is no longer replenished at the same rate. Gradually, the upper layers begin to cool, the change subtle at first but persistent. This cooling alters the density of the water, affecting how layers mix and how nutrients move between depths. Processes that once followed stable gradients begin to shift, introducing new variability into the system. The atmosphere above continues to hold its suspended load, prolonging the period of reduced light. Days pass without the return of full brightness, and the ocean adjusts to this extended dimness. The contrast between surface and depth lessens slightly, as both exist under conditions that are no longer defined by strong illumination. In some regions, the sinking of organic material slows, reflecting the reduced production at the surface. In others, particles carried from land and atmosphere contribute new inputs, changing the composition of what settles through the water column. These subtle changes accumulate, influencing chemical conditions in ways that extend beyond the visible loss of light. The ocean remains in motion, its currents continuing to circulate water across vast distances, yet the character of its surface has changed. Where there had once been a continuous exchange of light and life, there is now a muted interface, shaped by absence rather than abundance. The patterns that once depended on steady illumination begin to reorganize under these new constraints, forming a different kind of equilibrium, quieter and less defined. The change does not arrive as a single disappearance, but as a gradual thinning that begins at the smallest scale and moves upward through every layer of life. In the dimmed surface waters, where microscopic organisms once formed a continuous living field, the reduction becomes more pronounced with each passing interval. The foundation that had quietly sustained the ocean begins to loosen, its continuity breaking into scattered patches that no longer connect in the same way. Phytoplankton, once abundant enough to support entire chains of life, now exist in diminished numbers across wide regions. Their decline alters the availability of energy at its source, creating gaps that cannot be easily filled. These organisms had converted light into nourishment with steady reliability, and without that constant input, the system above them begins to adjust to a quieter, more limited flow. Small consumers, which depend directly on this primary production, encounter an environment where food is no longer consistently present. Their movements shift as they search for remaining concentrations, forming temporary clusters that dissolve as quickly as they gather. Some persist by adapting to reduced intake, while others fade as their requirements exceed what the environment can provide. As this imbalance moves upward, the effects become more visible in larger organisms. Fish and invertebrates that once fed on abundant prey now encounter intervals of scarcity. Their growth slows, reproduction becomes less frequent, and populations begin to contract. The relationships that had once been stable, defined by predictable exchanges of energy, lose their consistency. Predators, which had depended on these intermediate levels, continue to move through the ocean with the same patterns for a time. Their bodies carry the memory of a system that had always supported them, and for a short period, that momentum sustains their presence. Yet the reduction beneath them continues, gradually removing the prey they rely on. Encounters become less frequent, and the effort required to find food increases. The change spreads without abrupt boundaries. It moves through the ocean as a series of linked adjustments, each level responding to the diminishing support below it. There is no single moment when the system collapses, but rather a continuous process in which each connection weakens, one after another. In some regions, isolated pockets of productivity remain, supporting temporary concentrations of life. These areas become focal points where organisms gather, drawn by the limited availability of resources. Yet these clusters are unstable, shifting as conditions change, unable to restore the broader continuity that once existed. Larger predators begin to reflect the cumulative effects of this decline. Their ranges expand as they search for sufficient food, moving beyond the boundaries they had once occupied. Energy expenditure increases, while intake becomes less certain. Over time, this imbalance leads to a reduction in their numbers, not through sudden disappearance, but through a gradual thinning, similar to what occurred at smaller scales. Across the ocean, entire lineages begin to recede. Some species persist in reduced forms, while others fade completely, unable to adapt to the altered conditions. The loss is not evenly distributed, and different regions experience varying degrees of change, but the overall pattern remains consistent. The structure that had once connected all levels of life becomes fragmented, its pathways interrupted. What remains is a system still in motion, but no longer supported by the steady flow that had defined it. Energy moves through fewer channels, and those that remain are less stable, more susceptible to further change. The ocean continues to hold life, yet its internal connections have been reshaped, leaving a quieter, more uncertain network in place of what had once been continuous. Absence begins to take shape not as an immediate void, but as a gradual recognition that certain movements no longer pass through the water. Paths once traced by large bodies remain undisturbed, their routes fading into stillness as time continues without them. The ocean holds their memory for a while, in patterns of space and expectation, before even those traces begin to soften. Among the largest of these presences were the marine reptiles that had moved through open waters and along continental margins with steady authority. Mosasaurs, with their elongated forms and powerful strokes, had occupied vast ranges, while plesiosaurs, with their distinct proportions, had moved through different layers of the ocean with equal familiarity. Their roles had been refined over long intervals, fitting precisely into a system that had supported their continued existence. As the changes within the ocean deepen, these animals encounter conditions that no longer sustain them. Their dependence on stable food sources becomes a constraint, and as those sources diminish, their ability to maintain energy balance weakens. The distances they must travel increase, while the returns from those movements become less certain. Over time, their populations begin to contract, not uniformly, but with a pattern that reflects the uneven nature of the changing ocean. Younger individuals, which require consistent nourishment to reach maturity, face greater challenges. Growth slows, survival rates decline, and fewer reach the stages necessary to reproduce. The continuity that once allowed these species to persist across generations begins to fragment. Each loss contributes to a gradual thinning, reducing their presence across the regions they once occupied. At the same time, ammonites, which had formed a vast and intricate component of marine life, begin to disappear. Their coiled shells, once common across many environments, become less frequent in the water column. These organisms had existed in immense numbers, their life cycles closely tied to the broader system of production and consumption. As that system shifts, their ability to maintain populations declines rapidly. Unlike some other groups, ammonites do not persist in reduced forms. Their decline leads to complete disappearance, leaving no surviving lineages to continue their presence. The spaces they occupied within the food web remain unfilled for a time, creating gaps that alter the flow of energy and interaction among remaining species. With the loss of both large reptiles and abundant mid-level organisms, the structure of the ocean changes in a more visible way. Predatory roles that had once been consistently occupied are left without direct successors. The absence of these dominant figures alters the behavior of other species, which adjust to a system where the pressures and interactions they once experienced are no longer present in the same form. The ocean does not become empty, but its hierarchy becomes less defined. Without the regular presence of its largest hunters, patterns of movement and distribution shift. Some species expand into new areas, while others retreat, responding to conditions that no longer follow previous arrangements. These changes unfold over spans of time that allow the process to remain gradual, yet the outcome is clear. Entire groups that had defined the character of the ocean for millions of years are no longer part of its living system. Their disappearance marks the end of lineages that had once seemed inseparable from the marine world. What remains is an ocean still in motion, still inhabited, yet altered in its composition. The roles once held by these giants do not immediately pass to others. Instead, the system continues without them, carrying forward a different arrangement of life, shaped by the absence of those that had long defined its upper layers. Long after the first disturbances have passed through the surface and coastlines have settled into new shapes, a quieter transformation begins to take hold within the water itself. It does not move as a visible wave or a sudden shift, but as a gradual alteration in the composition of the ocean, carried by particles and gases that continue to arrive from above. Fine material, lifted into the atmosphere during the impact and its aftermath, begins to descend across the globe. These particles fall slowly, spreading over vast areas of open water, settling through the upper layers and drifting toward the depths. Some remain suspended for extended periods, altering the clarity of the water, while others accumulate along the seafloor, forming thin layers that mark this moment in time. Alongside this steady descent, the chemistry of the ocean begins to respond to changes in the atmosphere. Gases released during the event dissolve into the surface waters, interacting with existing compounds and shifting the balance that had long remained stable. Carbon dioxide, present in elevated amounts, reacts with seawater to form carbonic acid, subtly lowering the pH of the ocean. This change does not happen uniformly, and its effects vary across regions and depths, but the overall direction remains consistent. The water becomes slightly more acidic, altering the conditions under which many organisms function. These shifts are not immediately visible, yet they influence processes that occur at the smallest scales, where life depends on precise chemical interactions. For organisms that build shells or skeletons from calcium carbonate, the change introduces a new difficulty. The availability of carbonate ions, essential for constructing and maintaining these structures, becomes reduced in more acidic conditions. As a result, the formation of shells requires more energy, and in some cases, existing structures begin to weaken or dissolve. These effects ripple through populations of small marine organisms, many of which had played essential roles within the broader system. Their reduced ability to maintain physical structures influences their survival, growth, and reproduction. Some adapt to the changing conditions, adjusting their processes to accommodate the new chemistry, while others decline as the balance shifts beyond their tolerance. The impact of these chemical changes extends beyond individual species. As populations of shell-forming organisms decrease or alter their behavior, the interactions that depend on them begin to shift. Predators that rely on them as a food source encounter changes in availability, while the materials they contribute to the ocean, both living and after death, become less abundant. In deeper waters, where conditions change more slowly, the effects are moderated but still present. The gradual mixing of surface and deeper layers carries altered chemistry downward, introducing these changes into regions that had once remained relatively constant. The pace is slower, yet the direction remains aligned with what has already begun above. Throughout the ocean, life continues to move and adjust, but the environment itself now carries a different set of constraints. Processes that once occurred with ease now require greater effort or yield different outcomes. The balance between organisms and their surroundings becomes more dynamic, shaped by a chemistry that no longer follows its previous stability. This transformation unfolds without sharp boundaries or clear endpoints. It spreads through the ocean as a subtle but persistent shift, influencing every layer it reaches. The water remains familiar in appearance, yet within it, The conditions that support life have been quietly redefined, setting the stage for further changes to emerge over time. What remains is not a still ocean, but one where movement has become harder to notice, as if the rhythms that once filled the water have softened beyond easy recognition. The currents continue their long, steady paths, yet the life that once traced those paths has grown sparse, leaving wider spaces between each passing form. Across the open waters, the absence of large bodies becomes increasingly apparent. Where expansive regions once held the steady presence of dominant animals, there are now stretches of water that pass without interruption. The surface reflects light in muted tones, and beneath it, the familiar silhouettes that once moved through layered depths are no longer part of the daily pattern. This reduction does not arrive as a sudden clearing, but as a gradual thinning that continues over extended time. Each passing interval carries fewer encounters, fewer overlapping movements, fewer signs of the dense interactions that had once defined the ocean's upper layers. The system remains active, but its activity has shifted toward a quieter state, where processes unfold with less visible expression. In these conditions, ecosystems begin to settle into lower levels of activity. Energy continues to move, but through fewer pathways and at a slower pace. The connections that remain are more fragile, dependent on limited exchanges that no longer sustain the same complexity. Organisms adjust by reducing their movements, conserving what they can within an environment that offers less in return. The open ocean, once marked by continuous interaction, takes on a different character. It becomes a space where distance is more pronounced, where life appears in isolated instances rather than in continuous patterns. A single movement carries further significance, not because it is larger or more dramatic, but because it stands alone within a broader stillness. Near the surface, the water column reflects this change through its relative clarity. With fewer organisms occupying the upper layers, there is less disruption to the passage of light and less particulate matter generated by biological activity. The water feels more open, its structure defined less by life and more by the physical processes that continue beneath it. Deeper layers mirror this shift in their own way. The steady descent of organic material from above becomes less frequent, altering the conditions for organisms that rely on this slow supply. Activity continues, but at a reduced scale, with fewer inputs reaching these depths over time. The balance between consumption and availability adjusts accordingly, shaping a system that functions with less intensity. Throughout the ocean, this quieter state persists without sharp transitions. It is not defined by emptiness, but by reduction, by the absence of what had once been common. Life remains present, yet its distribution has changed, becoming more scattered and less connected across distances. In this environment, time seems to extend further between events. Interactions that once occurred in close succession now unfold with greater intervals, giving the ocean a sense of expanded space. The continuity of movement is replaced by moments that arise and fade without immediate repetition. The ocean continues to exist as a complete system, yet its character has shifted toward a more subdued form. It carries within it the traces of what has passed, while settling into a state defined by fewer connections and quieter motion. Far below the dimmed surface, beyond the reach of fading light, the ocean holds a different kind of continuity, one shaped by distance from the disturbances above. In these depths, change arrives more slowly, filtered through layers of water that soften its intensity. The conditions here, long defined by stability, remain closer to their earlier state, even as the upper ocean continues to shift. Temperature, which had always varied little in these regions, maintains its steady range. The cold, dense water preserves an environment where fluctuations are minimal and where life has adapted to constancy rather than variation. Organisms that inhabit these depths are accustomed to limited resources and gradual processes, their existence shaped by patience and efficiency. The absence of direct sunlight, which defines the deep ocean under all conditions, becomes less of a distinction as the surface dims above. The difference between layers narrows slightly, not through the addition of light below, but through its reduction above. For the organisms that live in darkness, this change does not disrupt their primary means of survival. They continue to rely on alternative sources of energy, including the slow descent of organic material and, in some regions, chemical processes near the seafloor. As the supply of material from above decreases, these communities adjust within the limits they have always known. The flow of nutrients becomes less abundant, yet not entirely absent. Organisms reduce their activity, extending the intervals between feeding and conserving energy in ways that align with their long-established adaptations. Survival here does not depend on rapid change, but on the ability to endure reduced conditions over extended periods. Isolation plays a significant role in this persistence. The physical separation between deep and surface environments limits the immediate impact of events that reshape the upper ocean. While changes in chemistry and circulation eventually reach these depths, they do so gradually, allowing time for adjustment. This separation acts as a form of protection, not by preventing change entirely, but by moderating its pace and intensity. Within these deep regions, a variety of organisms continue their existence with little outward sign of disruption. Some move slowly across the seafloor, while others remain suspended in the water column, conserving energy between feeding opportunities. Their life cycles proceed at a pace that reflects the stability of their environment, with growth and reproduction occurring over extended timescales. Hydrothermal vent communities, where chemical energy supports unique forms of life, maintain their localized systems with relative continuity. The processes that sustain them originate from within the earth, rather than from the surface, providing a level of independence from changes above. These environments remain active, their organisms continuing to thrive in conditions that have always been defined by extremes. The deep ocean, in this period, becomes a refuge not through abundance, but through consistency. While the upper layers experience fragmentation and loss, these depths offer a form of persistence rooted in long-term stability. The organisms that inhabit them do not escape change entirely, but they encounter it in a way that allows for gradual adjustment rather than immediate disruption. Over time, this early advantage contributes to their continued presence within the ocean. As other regions struggle to maintain their structures, the deep ocean retains elements of continuity that will later support the broader recovery of marine systems. For now, it remains a quiet domain, where life endures within boundaries that have shifted less dramatically, holding on through the slow passage of change. In places where the water appears nearly empty to the eye, life begins again at a scale too small to follow directly, unfolding within thin layers and drifting currents. The vast structures that once defined the ocean have faded, yet within this quieter environment, microscopic organisms continue to divide, persist, and gradually expand their presence. These forms of life, simple in structure yet highly adaptable, respond quickly to changing conditions. Their reproduction does not depend on long intervals or complex development. Instead, they multiply through rapid cycles, each division producing new individuals capable of continuing the same process. Where conditions allow even a slight advantage, their numbers begin to increase, filling spaces left open by earlier losses. In the upper layers, where light returns in faint and inconsistent patterns, certain microorganisms resume the process of photosynthesis. Even reduced illumination provides enough energy for some species to begin rebuilding populations. Their growth is not immediate or uniform, but it is persistent, spreading outward from regions where conditions are most favorable. Other microorganisms, less dependent on light, draw energy from chemical sources within the water. These organisms continue to function even when surface conditions remain unstable, contributing to the gradual reestablishment of biological activity. Together, these different forms of microscopic life create a network of processes that begin to restore movement within the system. As their populations expand, the effects begin to extend beyond their immediate scale. The presence of these organisms increases the availability of organic material, providing a renewed source of energy for slightly larger consumers. Small zooplankton begin to find sustenance once more, their feeding patterns becoming more consistent as microscopic life becomes more widespread. This rebuilding does not occur evenly across the ocean. Certain regions support faster recovery, while others remain sparse for longer periods. The distribution of microorganisms reflects local conditions, including temperature, nutrient availability, and the lingering effects of earlier disruptions. Yet across these variations, a common pattern emerges, one of gradual increase and spreading continuity. The importance of these small forms lies not only in their numbers, but in their position within the system. By re-establishing the base of the food chain, they create the conditions necessary for more complex interactions to return. Each layer that forms above them depends on their continued presence, making their recovery a foundational step in the broader transformation of the ocean. Their influence extends into the chemistry of the water as well. Through their metabolic processes, they contribute to the cycling of elements, affecting the balance of carbon, oxygen, and other essential components. These changes, though subtle, help shape the environment in ways that support further biological activity. Over time, the accumulation of these small processes leads to a visible shift in the character of the ocean. Areas that had remained quiet begin to show signs of renewed life, not through the return of large organisms, but through the steady presence of microscopic activity. The water, once defined by absence, begins to carry a different quality, shaped by the unseen work occurring within it. This phase of recovery remains largely invisible, yet it holds lasting significance. The organisms involved do not dominate the ocean in a visible sense, but they guide its direction by restoring the fundamental processes that sustain life. Through their persistence and adaptability, they begin to reshape the system from its smallest components, setting in motion changes that will continue to unfold over extended spans of time. Along the edges where land meets sea, the character of the ocean begins to vary in subtle but important ways. These regions, shaped by shifting sediments, freshwater input, and irregular coastlines, do not follow the same patterns as the open water. Within their shallower depths and sheltered contours, conditions form that differ just enough to offer moments of persistence. In these coastal zones, the interaction between ocean and land creates environments that are more complex in structure. Estuaries, where rivers meet the sea, carry nutrients and organic material that continue to enter the system even as broader processes remain disrupted. The mixing of fresh and salt water produces gradients that support a range of organisms adapted to changing conditions. Sheltered bays and inlets provide further variation. Their partial enclosure reduces the intensity of large-scale disturbances, allowing water to settle in ways that differ from the open ocean. Circulation within these areas is often slower and more contained, creating pockets where biological activity can continue at reduced but stable levels. Within these spaces, certain forms of life find conditions that remain within their limits of tolerance. Small fish, invertebrates, and microorganisms persist in numbers that are higher than in surrounding regions. The availability of nutrients, combined with relative protection from broader shifts, supports ongoing cycles of feeding and reproduction, even as these cycles remain subdued compared to earlier periods. Vegetated coastal habitats, including early forms of seagrass beds and other shallow marine plant communities, contribute to this stability. Their presence helps anchor sediments, reduce water movement, and create microenvironments where organisms can find shelter. These areas act as quiet centers of activity where life continues in forms that are less dependent on large-scale patterns. The influence of these refuges does not extend uniformly across the globe. Some coastlines provide more protection than others, depending on their shape, orientation, and connection to inland systems. As a result, survival becomes uneven, with certain regions maintaining higher levels of biological continuity, while others reflect the broader decline. This patchwork distribution creates a fragmented ocean where areas of relative persistence are separated by expanses of reduced activity. Movement between these regions becomes more significant, as organisms that can travel short distances may encounter conditions that support their survival. These transitions are not always successful, yet they contribute to the gradual redistribution of life across the changing system. Within each refuge, interactions continue in a more localized form. Food chains remain shorter, and the number of connections between species is reduced, yet the essential processes persist. Energy enters, circulates, and supports life, even if at a diminished scale. These systems do not replicate the complexity of earlier oceans, but they maintain enough structure to endure. Over time, these coastal environments contribute to the broader pattern of recovery. The organisms that persist within them carry forward genetic and ecological traits that will later influence the rebuilding of larger systems. Their continued presence ensures that the ocean does not begin again from absence, but from scattered points of continuity. The margins of the sea, often overlooked in the vastness of the ocean, become places where survival holds its ground. In their shifting waters and sheltered spaces, life continues in fragments, forming a network of persistence that spans the globe in uneven but enduring patterns. Time extends in a way that cannot be measured by brief intervals, unfolding instead across spans so long that change becomes visible only through accumulation. The ocean, still shaped by earlier losses, begins a process that does not aim to restore what once existed, but to form something that can persist under altered conditions. In the absence of rapid shifts, life continues through slow adjustment. Populations that endured begin to expand gradually, their growth limited but steady. Each generation adds a small layer of continuity, extending the presence of species that manage to remain through the most difficult intervals. These increases are not uniform, and they do not occur everywhere at once, yet they mark the beginning of a broader pattern. Biodiversity, once sharply reduced, starts to return in subtle increments. New variations appear within existing lineages, reflecting small changes in form and behavior that allow organisms to use available resources more effectively. Over extended periods, these variations accumulate, leading to the emergence of distinct species that occupy roles shaped by the current state of the ocean. The rebuilding of ecological relationships follows this gradual expansion. Organisms begin to interact in more consistent ways, forming connections that had previously weakened or disappeared. Predator and prey relationships reestablish themselves in simpler forms, then grow more layered as additional species enter the system. Each connection strengthens the overall structure, contributing to a network that becomes increasingly stable over time. Energy flow through the ocean begins to regain continuity. The base, supported by microscopic life, sustains larger populations, which in turn support higher levels. These pathways remain less complex than those that existed long before, yet they become more reliable, allowing ecosystems to function with greater consistency. Movement within the system, both in terms of organisms and nutrients, reflects this renewed stability. Environmental conditions also begin to settle into patterns that persist across longer spans. Temperature gradients, circulation pathways, and chemical balances adjust gradually, influenced by both biological activity and physical processes. These factors interact to create conditions that support the continued presence of life, even if they differ from earlier states. As this process unfolds, the ocean does not move toward a fixed endpoint. Instead, it continues to evolve, shaped by ongoing interactions between organisms and their environment. Stability, in this context, does not mean unchanging conditions, but rather the presence of systems that can endure variation without collapsing. In different regions, recovery progresses at different rates. Some areas regain complexity more quickly, while others remain simpler for longer periods. These variations contribute to a diverse global pattern where ecosystems develop along multiple pathways, each influenced by local conditions and histories. The passage of millions of years allows these changes to accumulate into a new structure. Life becomes more abundant, interactions more frequent, and the overall system more cohesive. The ocean, once fragmented, begins to exhibit a form of continuity that supports a wide range of organisms. Through this extended interval, the character of the ocean shifts from one defined by reduction to one shaped by gradual rebuilding. Each addition, each connection, and each adjustment contributes to a system that becomes more stable not through sudden transformation, but through the steady accumulation of countless small changes. Forms that had once moved in supporting roles begin to occupy wider ranges, extending into spaces that had remained beyond their reach. In the changing ocean, fish increase not only in number, but in presence, appearing across depths and regions where larger predators had once defined the structure. Their movements become more frequent, more varied, tracing new paths through water that now holds fewer constraints. These expansions do not occur all at once. They unfold gradually as populations adjust to conditions that favor flexibility and rapid response. Many fish species possess characteristics that allow them to adapt to shifting environments, including shorter generation times and a wide range of feeding strategies. As a result, they begin to explore ecological roles that had previously been unavailable, moving into positions left open by earlier losses. In open waters, schools of fish grow larger and more widespread, forming coordinated patterns that shift with currents and available resources. Their collective movement provides both protection and efficiency, allowing them to navigate environments where stability has not fully returned. Within these groups, variation in size and behavior begins to emerge, reflecting subtle differences that influence survival. Along continental margins and within remaining structured habitats, fish diversify further. Some develop streamlined forms suited for sustained swimming, covering greater distances in search of food. Others adopt shapes that allow them to maneuver within complex environments, moving through narrow spaces or remaining close to the seafloor. These variations are not isolated developments, but part of a broader pattern in which different forms arise to match different conditions. Feeding strategies expand alongside these physical changes. Certain species become more specialized, focusing on particular types of prey or methods of capture. Others retain a more general approach, consuming a wide range of available food sources. This diversity in feeding allows fish populations to occupy multiple levels within the developing food web, contributing to a system that becomes increasingly layered. Predatory roles, once dominated by larger marine reptiles, begin to shift toward these expanding fish populations. While no single species immediately replaces the scale or influence of those earlier predators, groups of fish collectively fill aspects of those roles. Some grow larger, developing the ability to pursue and capture substantial prey, while others rely on speed and coordination to hunt in groups. Reproductive strategies also support this expansion. Many fish produce large numbers of offspring, increasing the likelihood that some will survive under variable conditions. This approach allows populations to respond quickly to opportunities, spreading into regions where resources become available. Over time, these repeated cycles of reproduction and survival contribute to the steady increase in both numbers and diversity. As these changes accumulate, the presence of fish becomes a defining feature of the recovering ocean. Their interactions with one another and with other organisms create new patterns of movement and exchange. Energy flows through these populations in ways that begin to resemble more complex systems, supporting a wider range of life. The diversity that emerges during this period forms the foundation for future developments. Many of the lineages that arise will continue to evolve, giving rise to forms that persist into later eras. Their adaptability, shaped during this time of change, allows them to remain central to marine ecosystems as conditions continue to shift. Through gradual expansion and diversification, fish move from supporting positions into more prominent roles. Their growing presence reflects not a return to what had existed before, but the establishment of a new structure, one in which they become a central component of the ocean's evolving system. At the boundary where rivers widen and merge with the sea, movement begins to follow unfamiliar patterns, not only within the water, but at its edge. Small land mammals approach these shifting margins, drawn by resources that gather where freshwater and saltwater meet. Their presence is tentative at first, shaped by brief forays rather than permanent residence. These early explorers do not yet belong to the ocean. Their bodies remain suited for life on land, with limbs designed for walking and lungs adapted for air. Yet the environments they enter offer new opportunities, including access to food that exists beyond the shoreline. Shallow waters provide a space where they can wade, swim for short distances, and return to land with relative ease. Over time, repeated visits begin to influence their behavior. Movements in water become more efficient, as individuals that can swim with greater control gain access to resources others cannot reach. Subtle changes in posture and limb use begin to appear, reflecting the demands of moving through a denser medium. These adjustments are not sudden transformations, but gradual shifts shaped by repeated interaction with the aquatic environment. Feeding habits also begin to change. Some mammals learn to capture prey within the water, using their jaws in ways that differ from their terrestrial behavior. Others forage along the margins, taking advantage of organisms that thrive in these transitional zones. This expansion in diet supports further exploration, encouraging continued use of aquatic spaces. As generations pass, certain lineages spend increasing amounts of time in the water. Their bodies begin to reflect this shift, with modifications that improve swimming and reduce resistance. Limbs that once supported weight on land start to function more effectively as paddles, while body shapes become more streamlined. These changes occur incrementally, each adaptation building upon earlier variations. Diving, initially brief and limited, becomes more practiced. The ability to remain submerged for longer periods provides access to deeper resources, expanding the range of environments these animals can use. Physiological adjustments support this behavior, allowing for more efficient use of oxygen and greater tolerance of pressure changes. These capabilities develop gradually, aligned with the increasing reliance on aquatic habitats. Despite these changes, the connection to land is not immediately lost. Early marine mammal ancestors continue to return to shore for rest and reproduction, maintaining a link between environments. This dual existence shapes their evolution, balancing the demands of both land and water as adaptations continue to accumulate. Within the broader ocean system, their presence introduces a new form of interaction. Unlike fish, which rely entirely on aquatic respiration, these mammals carry air with them, surfacing regularly as part of their movement. This pattern creates a rhythm distinct from other marine organisms, adding another layer to the developing complexity of the ecosystem. Their role remains limited at first, yet it marks the beginning of a significant shift. The transition from land to sea represents a new pathway, one that will lead to forms fully adapted to life in the ocean. These early stages, defined by partial adaptation and continued connection to land, establish the foundation for that transformation. As these mammals continue to explore and adapt, their presence becomes more consistent within coastal and shallow marine environments. The changes they undergo do not restore what had been lost, but they contribute to the emergence of new possibilities, shaping a direction that will influence the ocean's evolving structure over long spans of time. In the widening spaces left by earlier losses, movement returns with a different kind of precision, shaped by forms that had endured through the transition. Among these, sharks continue to move through the water with steady purpose, their presence becoming more pronounced as the structure of the ocean reorganizes around them. Their survival is not accidental, but tied to traits that allow them to persist through changing conditions. Flexible diets, efficient sensory systems, and the ability to travel across large distances support their continued existence. As other dominant predators fade, these characteristics place sharks in a position where they can expand into roles that had once been occupied by larger marine reptiles. This expansion unfolds gradually. Shark populations increase in regions where prey becomes available, their movements extending into areas that had previously been less central to their activity. Different species begin to occupy different depths and environments, spreading across coastal zones, open waters, and deeper layers. Their distribution reflects both opportunity and adaptation, shaped by the evolving structure of the ocean. As they move into these roles, their hunting strategies begin to diversify. Some species rely on speed, using streamlined bodies to pursue prey over distance, while others adopt slower, more deliberate approaches, conserving energy and striking with precision. Sensory adaptations, including the ability to detect electrical signals and subtle changes in water movement, allow them to locate prey even in conditions where visibility is reduced. Group behavior emerges in certain contexts, with multiple individuals converging on areas of higher productivity. While many sharks remain solitary, these temporary aggregations reflect a flexibility in behavior that supports their expansion. Each interaction contributes to a shifting pattern of predation, where strategies are not fixed but responsive to conditions. The prey base they depend on also begins to change. With fish populations increasing and diversifying, sharks find new sources of food that support their growth. This relationship develops into a dynamic balance where predator and prey influence each other's distribution and behavior. The presence of sharks shapes the movements of other organisms, introducing new patterns into the recovering ecosystem. As these processes continue, the hierarchy of predators within the ocean begins to take on a different form. No single species dominates in the way earlier reptiles once had. Instead, a range of shark species occupies various levels within the upper tiers of the food web. This distribution creates a more varied structure, where influence is shared across multiple forms rather than concentrated in a few. Physical adaptations accompany these changes. Variations in body shape, tooth structure, and size reflect the different roles that sharks begin to fill. Some develop broader heads suited for crushing prey, while others retain narrow forms optimized for rapid pursuit. These differences are not isolated, but part of a broader diversification that allows sharks to interact with the environment in multiple ways. Over time, their presence becomes a defining feature of the ocean's upper levels. Their movements, interactions, and influence contribute to the emerging stability of the system, shaping how energy flows through the food web. The roles they occupy are not identical to those that existed before, but they provide a new framework for predation within the changing ocean. Through persistence and adaptation, sharks become central to this evolving structure. Their expansion reflects a shift in how dominance is expressed, moving away from singular control toward a more distributed arrangement that continues to develop across the recovering marine world. Speed begins to define encounters in a way that had not shaped the ocean before, altering how movement unfolds between predator and prey. Where earlier hunters relied on size and sustained presence, the emerging pattern favors quick acceleration, sudden turns, and brief moments of contact that determine the outcome of each interaction. Fish and sharks, already expanding into wider roles, now establish a different style of predation across the ocean. Their bodies, lighter and more flexible than those that once dominated, allow for rapid changes in direction and pace. This agility reshapes the spaces in which they operate, turning open water into a dynamic field where movement itself becomes a central strategy. Pursuit takes on new forms. Some predators rely on bursts of speed, closing distances in short, decisive movements that leave little time for escape. Others use endurance, maintaining a steady pace that gradually narrows the gap between themselves and their targets. These approaches coexist, reflecting a diversity of methods that allow predators to adapt to varying conditions and prey behaviors. Ambush also becomes more refined. Rather than relying solely on concealment within physical structures, predators begin to use timing and positioning as key elements of their strategy. They align themselves with currents, shadows, or the movement of other organisms, waiting for moments when their presence remains undetected until the final instant. This approach reduces the need for prolonged chases, conserving energy while increasing effectiveness. The sensory abilities of these hunters support these changes. Detection of subtle vibrations, chemical traces, and electrical signals allows them to locate prey with precision, even in environments where visibility is limited. These capabilities create a layer of interaction that extends beyond sight, enabling predators to respond to signals that travel through the water in ways that are less immediately apparent. As these methods spread, prey species begin to adjust in response. Their movements become less predictable, with changes in schooling behavior, depth preference, and timing of activity. Some rely on coordinated group motion to reduce individual risk, while others adopt more solitary patterns that make detection more difficult. Each adjustment reflects the shifting pressures within the system, contributing to a continuous exchange between predator and prey. The overall dynamic of survival becomes more fluid. Encounters are often brief, with outcomes determined in moments rather than extended sequences. This shift influences energy use, reproduction, and distribution as species adapt to a system where efficiency and responsiveness are critical. In different regions, variations in these interactions lead to distinct patterns of behavior. Coastal environments, open waters, and deeper layers each support different combinations of strategies, shaped by local conditions and available resources. This diversity contributes to a broader structure in which no single approach dominates entirely, but multiple methods coexist and evolve. The transition away from earlier forms of dominance becomes more apparent through these changes. The ocean no longer centers around a few large, persistent hunters, but around a network of agile predators that operate across multiple scales. Their presence creates a system where influence is distributed and where interactions occur across a wide range of speeds and intensities. Through these developments, the character of predation within the ocean is redefined. Movement becomes central, shaping how life interacts and persists. The patterns that emerge reflect a system in which adaptability and responsiveness guide survival, forming a structure that continues to evolve within the changing marine world. Stone begins to grow again beneath the surface, not through sudden formation, but through the quiet work of countless small organisms laying down structure over time. In warm, shallow regions where conditions allow, coral communities slowly return, assembling themselves piece by piece from living tissue and mineral framework. The process begins with scattered colonies, each forming in isolation where larvae settle onto stable ground. These early corals are not yet part of expansive reefs, but small clusters that expand outward through steady growth. Their skeletons, built from calcium carbonate, accumulate layer by layer, creating the first hints of structure in environments that had long remained simplified. Growth is slow and dependent on a balance of conditions. Temperature, light, and water chemistry must align within narrow ranges for corals to persist. Where these factors remain stable, colonies begin to extend, branching or spreading into shapes that reflect both their species and the movement of surrounding water. Each form contributes to the gradual construction of a three-dimensional habitat. As these structures develop, they begin to alter their immediate surroundings. The presence of coral creates surfaces where other organisms can attach, shelter, or feed. Small fish and invertebrates begin to appear, drawn by the opportunities provided by these emerging habitats. Their interactions, though limited at first, introduce new layers of activity into areas that had been relatively quiet. Symbiotic relationships also re-establish themselves within these systems. Microscopic algae living within coral tissues provide energy through photosynthesis, supporting growth in a way that ties the health of the reef to the clarity and quality of surrounding water. This partnership, delicate yet effective, allows corals to expand beyond what would otherwise be possible. Over extended periods, individual colonies merge into larger formations. These developing reefs begin to take on more recognizable shapes, rising from the seafloor and extending laterally across suitable areas. The complexity of their structure increases, with crevices, overhangs, and varied surfaces, creating a range of microenvironments. Within these growing reefs, biodiversity begins to increase. Different species occupy different niches, each finding a place within the evolving structure. Some remain close to the coral surface, while others move through the spaces between formations. This distribution creates a layered system where interactions occur across multiple levels and scales. The presence of these reefs influences surrounding regions as well. They act as centers of productivity, supporting higher concentrations of life than adjacent areas. Organisms move between reef and open water, carrying energy and nutrients that contribute to broader ecological patterns. In this way, reefs become focal points within the recovering ocean. Despite this progress, the rebuilding remains gradual. Changes that appear significant at the scale of individual colonies unfold over long spans of time when viewed across entire regions. Growth is continuous but measured, shaped by conditions that can vary and occasionally limit expansion. As reefs continue to develop, they provide a foundation for increasing complexity within the ocean. Their structures support interactions that extend beyond their immediate boundaries, influencing patterns of movement, feeding, and reproduction among a wide range of species. Through this slow accumulation, coral ecosystems begin to reclaim their role as centers of diversity and structure. They do not replicate what once existed, but they establish new formations that support a different arrangement of life, contributing to the ongoing transformation of the marine world. Connections begin to weave themselves back into the ocean, not all at once, but through the gradual alignment of countless interactions that start to hold their shape. What had once been scattered and uncertain begins to organize into patterns that repeat with greater consistency, forming layers that extend through the water column. At the base, microscopic life continues its steady work, supporting increasingly stable populations of small consumers. These organisms, no longer confined to isolated patches, begin to form broader distributions that link regions together. Their presence allows energy to move more reliably upward, feeding into levels that had once struggled to maintain continuity. Above them, fish populations expand into more defined roles, interacting with one another in ways that reflect a growing structure. Some species specialize in feeding on plankton, while others focus on smaller fish or invertebrates. These distinctions reduce overlap and competition, allowing multiple groups to coexist within the same environment. Each role contributes to a network that becomes more organized over time. Predator and prey relationships begin to settle into patterns that repeat across regions. Encounters, once shaped by unpredictability, now follow more consistent dynamics. Prey species develop behaviors that balance risk and access to resources, while predators refine their strategies to match these adaptations. This ongoing exchange creates a system where interactions become more predictable even as they remain dynamic. As these relationships stabilize, ecological specialization increases. Species evolve traits that allow them to focus on specific resources or habitats, reducing direct competition and enhancing efficiency. Some occupy narrow depth ranges, while others adapt to particular temperature conditions or types of prey. These specializations contribute to the formation of distinct niches, each supporting a unique set of organisms. The result is a layering of the food web, where different levels interact in coordinated ways. Energy flows from primary producers through multiple intermediate stages before reaching top predators. This structure allows for greater resilience, as disruptions at one level can be absorbed or adjusted by others. The system does not return to its previous form, but it gains a new stability rooted in diversity and connection. Physical environments reflect this increasing complexity. Coral formations, coastal habitats, and open water regions each support their own networks of life, linked by movement and exchange. Organisms travel between these areas, carrying energy and nutrients that contribute to the overall balance of the ocean. These connections extend across distances, creating a system that is both local and global in its interactions. Behavioral patterns also become more varied. Migration, schooling, and territoriality emerge in forms that align with the developing structure of the ecosystem. These behaviors influence how species interact, shaping the distribution of life across regions and depths. Each pattern adds another layer to the system, contributing to its overall coherence. Over time, the accumulation of these changes leads to a more structured ocean. The fragmentation that once defined it gives way to a network of interconnected relationships where each part supports and is supported by others. This structure is not static, but it maintains a balance that allows life to persist and expand. The ocean, through these gradual adjustments, regains a sense of organization. Its systems, once reduced to scattered elements, now function as integrated wholes, shaped by the interactions that have slowly returned and taken hold across its vast and varied environments. Shapes begin to appear that do not follow familiar patterns, emerging from lineages that are adjusting in different directions at once. In the evolving ocean, form becomes more varied, reflecting a period where adaptation explores multiple possibilities rather than settling into a single path. These organisms arise from the gradual accumulation of small changes, each variation offering a slightly different way of interacting with the environment. Some develop elongated bodies suited for navigating narrow spaces or reducing resistance in open water. Others adopt compact forms that provide stability or protection, allowing them to persist in conditions where movement is less predictable. Behavior shifts alongside these physical changes. Feeding strategies diversify, with some species exploiting resources that had previously been underused. Others adopt new methods of movement, combining patterns of swimming, drifting, or remaining stationary in ways that align with their surroundings. These adjustments create a range of interactions that expand the possibilities within the system. Not all of these forms endure. Many represent temporary solutions suited to specific conditions that may not persist over long periods. As the environment continues to change, some lineages thrive for a time, increasing in number and influence, only to decline as conditions shift again. This pattern creates a dynamic landscape where dominance is often brief and localized. In certain regions, these unusual organisms become prominent, shaping the character of their environments. Their presence influences the behavior of other species, altering feeding patterns and movement within the surrounding community. Yet, this influence remains fluid as new forms continue to emerge and replace those that fade. The process reflects a kind of experimentation, though not guided by intention, but by the continuous interaction between organisms and their environment. Variations that provide even a small advantage can spread through populations, while those that do not are gradually lost. Over time, this filtering shapes the diversity that becomes more stable in later periods. Some of these new forms introduce features that will persist beyond this phase. Traits that enhance efficiency, resilience, or adaptability become integrated into lineages that continue to evolve. Others, while distinctive, do not extend beyond their immediate context, leaving behind only brief traces within the broader history of the ocean. The range of shapes and behaviors contributes to a system that is still defining its structure. Interactions remain flexible, with relationships between species adjusting as new forms appear and others disappear. This fluidity allows the ecosystem to explore different configurations, gradually moving toward arrangements that can endure more consistently. Across the ocean, this diversity creates a sense of variation that differs from earlier stability. Instead of long-established patterns, there is a shifting mosaic of forms, each representing a response to current conditions. The result is a landscape where change is ongoing and where the boundaries of possibility continue to expand. As time continues to pass, the influence of this period becomes embedded within the evolving system. The forms that persist carry forward elements of this experimentation, contributing to the complexity that will define later ecosystems. Those that do not endure remain part of the process that shaped the ocean during this interval, reflecting a phase where life explored multiple directions before settling into more stable patterns. The space once held by the largest hunters remains open, not as an empty absence, but as a region that no longer gathers around a single form of dominance. Movement continues through these upper layers, yet it is distributed differently, shaped by a range of species rather than centered on one lineage. Marine reptiles, which had once defined the structure of predation across wide areas, do not return to these waters. Their absence becomes a constant feature of the ocean, no longer a temporary gap but a permanent condition. The patterns they once maintained, built over long intervals, dissolve into a system that reorganizes without them. In their place, no direct equivalent emerges. There is no single group that mirrors their size, behavior, or influence. Instead, multiple lineages contribute to the roles that had once been concentrated. Sharks, large fish, and other predators each occupy parts of this space, creating a structure where influence is shared rather than singular. This distribution alters the way interactions unfold. Without a dominant figure shaping the behavior of entire regions, the ocean becomes a network of overlapping influences. Predators interact with prey in varied ways, and no single pattern extends across all environments. Each region reflects its own combination of species, shaped by local conditions and histories. The absence of large reptiles also influences the scale at which predation occurs. Encounters become more varied in size and duration, with fewer instances defined by overwhelming physical presence. Instead, interactions are often determined by speed, coordination, or strategy, reflecting the traits of the species that now occupy these roles. Over time, this new arrangement settles into a form of balance. It is not a return to what existed before, but a different configuration that supports stability through diversity. The presence of multiple predators reduces reliance on any single lineage, allowing the system to persist even as individual species change or decline. The identity of the ocean begins to shift in response to this transformation. What had once been a world where large reptiles defined the upper levels becomes a system characterized by a broader range of forms. This change is not marked by a single moment, but by the gradual accumulation of differences that alter how the ocean is structured and experienced. Other organisms adapt to this new context. Prey species respond to a wider variety of threats, developing behaviors that reflect the diversity of predators they encounter. Movement patterns, feeding strategies, and habitat use all adjust to align with a system that no longer follows earlier dynamics. The long absence of marine reptiles also shapes evolutionary pathways. Without their continued presence, other lineages expand into roles that would have remained unavailable. These developments influence the direction of change across the ocean, guiding how species evolve and interact over extended periods. Through these shifts, the ocean becomes something distinct from its earlier state. Its structure, interactions, and dominant forms reflect a new arrangement, one that carries forward the influence of past changes while establishing a different kind of continuity. The waters continue to move, filled with life that adapts and persists, yet the imprint of what is no longer there remains part of the system. It is present not as a visible feature, but as a defining absence that has reshaped the ocean into a different kind of world. Lines that once ran parallel begin to branch, creating a wider range of forms within a group that had already endured through earlier changes. Sharks, present through the transition, now diversify more fully, their lineage spreading into shapes and behaviors that resemble those seen in later oceans. This expansion is not sudden, but unfolds across long intervals as populations adapt to varied conditions. Different species emerge with distinct body plans, each suited to particular depths, temperatures, and types of prey. Some develop elongated forms for efficient cruising through open water, while others take on broader shapes that allow for maneuvering near the seafloor or within structured habitats. As these variations accumulate, recognizable lineages begin to form. Characteristics that define modern sharks, including specialized teeth, refined sensory systems, and more efficient swimming mechanics, become more consistent across groups. These features support their continued expansion, allowing them to occupy a wide range of ecological roles. In the upper levels of the ocean, certain shark species begin to assume positions that place them near the top of the food web. Their influence grows as they interact with a variety of prey, shaping patterns of movement and distribution across regions. This role does not rest on size alone, but on a combination of adaptability, perception, and persistence. Their sensory abilities contribute significantly to this position. The capacity to detect electrical signals, combined with acute sensitivity to movement and chemical traces, allows sharks to locate prey in diverse conditions. These capabilities extend their reach beyond what is immediately visible, enabling them to operate effectively across varying environments. Feeding strategies continue to diversify within this expanding group. Some species specialize in capturing fast-moving fish, relying on speed and coordination, while others focus on slower or more concealed prey, using different approaches suited to their targets. This range of strategies reduces direct competition, allowing multiple shark species to coexist within the same regions. Reproductive patterns also support their long-term presence. While many sharks produce fewer offspring compared to other marine organisms, their young often develop with a higher degree of independence. This balance between quantity and survival contributes to stable populations that can persist over extended periods. As these processes continue, sharks become a consistent feature of the ocean's upper levels. Their presence is not marked by a single dominant species, but by a collection of lineages that together shape the structure of predation. This distributed form of dominance allows for resilience, as changes affecting one group do not remove the role entirely. Over time, the diversity within sharks stabilizes into patterns that endure. The forms that prove most effective continue to persist, while others diminish, leaving behind a refined set of lineages that define the group. These patterns reflect a balance between variation and stability, shaped by ongoing interaction with the environment. The ocean, now structured around a range of predators rather than a singular presence, supports this continued diversity. Sharks move through these waters as both participants and influences, contributing to the dynamics that maintain balance within the system. Through gradual expansion and refinement, modern shark lineages establish themselves as enduring components of marine ecosystems. Their presence reflects a form of continuity that persists across changing conditions, shaping the ocean in ways that extend far beyond the period in which they first expanded. Along stretches of shallow coastline, where earlier forms once hesitated between land and water, a more complete transition begins to take shape. Certain mammal lineages, already accustomed to moving between these environments, extend their time in the ocean until the balance shifts entirely toward the water. Their bodies begin to change in ways that reflect this commitment. Limbs that once supported weight on land gradually transform into structures more suited for propulsion. Forelimbs flatten and broaden, functioning as flippers that guide movement through the water, while hind limbs diminish, losing their original role as the body becomes oriented toward swimming rather than walking. The spine grows more flexible in a different pattern, supporting undulating motion that moves the animal forward with efficiency. At the same time, body shape becomes more streamlined, contours smooth out, reducing resistance and allowing for sustained travel across open water. The distribution of mass shifts, aligning the body for balance within a fluid environment rather than on solid ground. These changes occur over many generations, each adjustment building on earlier variations that favor life in the ocean. Breathing remains tied to the surface, yet it becomes integrated into a fully aquatic rhythm. These mammals surface regularly, taking in air before returning below. Their lungs and circulatory systems adapt to support longer dives, storing oxygen and using it more efficiently. This ability allows them to move through deeper and more distant regions without constant return to land. Feeding behavior also transforms. Instead of capturing prey along the shoreline or in shallow waters alone, these animals pursue food within the ocean itself. Some develop methods of seizing individual prey, while others filter small organisms from the water in large volumes. These strategies reflect the diversity of resources available and the different ways in which they can be used. As this transition completes, the connection to land fades. Reproduction, which had once required a return to shore, shifts fully into the water. Young are born and raised within the ocean, their development adapted to conditions that remain entirely aquatic. This change marks a point where these mammals no longer depend on land for any stage of their life cycle. Within the broader marine system, their presence introduces a different kind of interaction. Unlike fish or other marine organisms, these mammals carry a complex nervous system shaped by their terrestrial origins. Their behavior reflects a capacity for learning, communication, and social structure that adds a new dimension to the ocean's developing complexity. Groups begin to form, with individuals moving together in coordinated patterns that extend beyond simple aggregation. These associations influence feeding, movement, and protection, creating networks of interaction that operate alongside existing ecological relationships. Communication, often through sound, becomes an important part of this structure, allowing individuals to maintain contact across distances where visibility is limited. The emergence of these fully aquatic mammals represents not only a change in form, but in the nature of interaction within the ocean. Their movements, behaviors, and relationships contribute to a system that continues to grow in complexity, shaped by a wider range of capabilities. Through this gradual transformation, mammals establish themselves as permanent inhabitants of the sea. Their presence reflects a new direction in the evolution of life, one that extends the influence of terrestrial lineages into the ocean, adding to the diversity and structure that define this evolving world. In the dim and often obscured waters, a different way of sensing begins to take hold, one that does not depend on light or proximity. Vibrations move through the ocean with ease, carrying information across distances that sight cannot reach, and certain animals begin to rely on these signals as a primary means of understanding their surroundings. Among the fully aquatic mammals, sound becomes central to movement and interaction. Their bodies, already adapted for life in the water, now incorporate structures that allow them to produce and receive acoustic signals with increasing precision. Pulses of sound travel outward, reflecting off objects and returning with subtle variations that reveal distance, size, and position. This process, known as echolocation, develops gradually as these mammals refine their ability to interpret returning echoes. At first, it supplements other senses, providing additional cues in environments where visibility is limited. Over time, it becomes more refined, allowing individuals to navigate complex spaces, locate prey, and avoid obstacles with a level of accuracy that transforms how they move through the ocean. The water itself supports this method of perception. Sound travels efficiently through the dense medium, maintaining its structure over long distances. This property allows signals to extend far beyond the immediate vicinity, connecting regions that might otherwise remain isolated. For the animals that use it, the ocean becomes a space defined not only by physical features, but by patterns of sound that shift and change with movement. Communication emerges as a natural extension of this ability. Marine mammals begin to produce a variety of vocalizations, each carrying information that can be interpreted by others of their kind. These sounds range from simple pulses to more complex sequences, forming a system that supports coordination, recognition, and social interaction. Groups maintain cohesion through these signals, even when individuals are separated by distance or obscured by the environment. Movement becomes coordinated through shared acoustic cues, allowing animals to travel, hunt, and respond to changes as a collective. This form of communication adds a new layer to the structure of the ecosystem, influencing how species interact with one another and with their surroundings. The influence of sound extends beyond these mammals. Other organisms respond to the presence of acoustic signals, adjusting their behavior in subtle ways. Some detect the vibrations and alter their movement to avoid detection, while others may use ambient sounds as cues for activity. The ocean becomes a more interconnected environment where information flows through channels that are not immediately visible. As this sensory layer develops, it reshapes the dynamics of survival. Predators that use sound gain access to prey that might otherwise remain hidden, while prey species adapt by refining their own responses to acoustic cues. This ongoing interaction contributes to a system where perception is no longer limited to sight or proximity, but includes a broader range of signals. Over time, the use of sound becomes an integral part of life in the ocean. It supports navigation through complex environments, facilitates communication across distances, and influences the relationships between species. This addition does not replace other forms of perception, but it expands the ways in which organisms engage with their world. Through this gradual development, the ocean acquires a new dimension, one defined by the movement of sound as much as by the movement of water. Within this dimension, life continues to adapt and interact, guided by signals that travel unseen yet shape the structure of the ecosystem in lasting ways. Far beneath the shifting layers above, there exists a region where change unfolds at a pace so slow it becomes almost imperceptible, a domain shaped more by continuity than by disruption. In these depths, the ocean maintains a steadiness that contrasts with the transformations occurring closer to the surface. Conditions here remain remarkably consistent over long spans of time. Temperature holds within a narrow range, influenced by the slow circulation of deep water that carries its properties across vast distances. Light does not reach these depths, and so the environment exists in a state that does not depend on the variations of day or season. Pressure remains constant, defining the physical limits within which life operates. Organisms that inhabit this realm are adapted to these stable conditions, their life processes unfolding at a measured pace. Growth occurs slowly, with individuals taking longer to reach maturity compared to their counterparts in more dynamic environments. Reproduction follows extended cycles, aligned with the limited availability of resources that reach these depths. Energy enters this system primarily through the gradual descent of organic material from above. Particles drift downward over time, providing a steady, though sparse, source of nourishment. This input does not fluctuate sharply, allowing organisms to rely on a consistent, if modest, supply. In some regions, chemical processes near the seafloor offer an additional source of energy, supporting communities that function independently of surface activity. The interactions within this environment reflect its stability. Movements are often slow and deliberate, conserving energy in a setting where excess expenditure cannot be easily replaced. Encounters between organisms occur less frequently, and the relationships that form are shaped by these constraints. Predation exists, but it unfolds at a pace that aligns with the overall rhythm of the system. Despite its relative isolation, the deep ocean remains connected to the broader marine world. Changes at the surface eventually influence these depths through the gradual mixing of water masses and the descent of materials. However, the effects arrive softened, spread over extended periods that allow for adjustment rather than immediate disruption. This stability provides a foundation for the ocean as a whole. While upper layers experience cycles of change and recovery, the deep sea offers continuity, maintaining processes that persist regardless of fluctuations above. Its consistent conditions support forms of life that endure through time, contributing to the overall resilience of the marine system. Over long intervals, the deep ocean accumulates subtle changes that reflect both internal processes and distant influences. These changes do not alter its fundamental character, but they contribute to a gradual evolution that aligns with the broader trajectory of the ocean. The balance between stability and slow adaptation defines this environment, allowing it to remain a constant presence within a changing world. The organisms that inhabit these depths continue their existence with little variation in their surroundings. Their adaptations, shaped over long periods, remain effective within the conditions that persist. This continuity allows them to endure through phases of transformation that affect other parts of the ocean more directly. In this way, the deep ocean serves as a quiet backbone, supporting the broader system through its stability. It does not draw attention through rapid change or visible activity, but through the steady presence of processes that continue without interruption, anchoring the ocean in a form of continuity that extends across immense spans of time. Across the uppermost layers, motion begins to reorganize, not as a sudden shift, but as a gradual reworking of pathways that guide water across the planet. Currents that once followed earlier patterns begin to adjust, influenced by changes in temperature, wind, and the distribution of land and sea. These movements, subtle at first, accumulate into a new circulation that reshapes the surface of the ocean. Temperature differences play a central role in this transformation. Variations between equatorial and polar regions begin to define gradients that influence how water moves. Warmer waters expand and remain near the surface, while cooler waters become denser and sink, setting in motion vertical exchanges that connect different layers. These processes interact with horizontal flows, creating a system that carries heat across vast distances. Wind patterns, shaped by atmospheric changes, guide surface currents into more defined routes. Persistent winds push water along coastlines and across open basins, establishing large-scale gyres that rotate slowly over time. These rotating systems organize the surface into regions with distinct characteristics, influencing how nutrients and organisms are distributed. As circulation becomes more structured, the distribution of marine life begins to shift. Species respond to changing temperatures and the movement of water masses, adjusting their ranges to align with conditions that support their survival. Some populations expand into newly suitable areas, while others contract or move toward regions that retain familiar conditions. Migration patterns emerge in response to these changes, with organisms traveling along currents that provide both transport and access to resources. These movements link distant regions, allowing species to occupy multiple environments over the course of their life cycles. The ocean becomes a network of connected pathways where movement is guided by the flow of water itself. Nutrient distribution also reflects the evolving circulation. In certain areas, upwelling brings deeper, nutrient-rich water toward the surface, supporting increased biological activity. In others, surface waters remain more isolated, leading to lower productivity. These variations create a patchwork of environments, each supporting different levels and types of life. The interaction between physical and biological processes strengthens as these patterns become more consistent. Currents influence where organisms gather, while the presence of life affects how energy and materials move through the system. This interplay contributes to a more integrated ocean, where structure arises from the combined effects of movement and interaction. Over extended periods, these changes lead to the formation of circulation patterns that resemble those present in later oceans. While not identical to modern systems, they establish the foundations upon which further refinement will occur. The pathways of water, once more variable, now follow routes that persist across longer timescales. This transformation influences not only the distribution of life, but the overall character of the ocean. Regions become defined by their conditions, with distinct communities forming in response to local environments. The surface, once shaped by earlier disruptions, now reflects a growing stability in its patterns of movement and exchange. Through this gradual reorganization, the ocean develops a circulation that supports both continuity and diversity. The flow of water connects distant regions while allowing for variation within each, creating a system that balances movement with structure. Within this evolving framework, life continues to adapt, guided by currents that shape the paths it follows across the changing sea. A sense of recognition begins to settle across the ocean, not as a return to what once existed, but as the emergence of patterns that align with those seen in later eras. The shifting processes that have unfolded over long spans of time now gather into arrangements that feel more continuous, more cohesive, and more enduring. In these waters, fish move in coordinated groups that reflect established roles within the ecosystem. Their presence spans from the surface to deeper layers, each species occupying positions shaped by feeding habits, movement, and environmental preference. Some travel in large schools, their synchronized motion forming shifting structures, while others remain solitary, navigating defined territories within the broader system. Sharks continue to move through these layers with steady purpose, their diversity now well established. Different species occupy distinct roles, from swift hunters of open water to forms adapted to life closer to the seafloor. Their interactions with prey contribute to a balance that regulates populations, maintaining stability within the evolving food web. Marine mammals, fully adapted to life in the ocean, add another dimension to this structure. Their movements across large distances connect different regions, while their behaviors introduce patterns of interaction that extend beyond simple feeding relationships. Groups form and disperse, their presence shaping the distribution of other organisms and contributing to the overall dynamics of the system. Together, these groups define the character of the ocean in a way that begins to resemble more familiar configurations. The absence of earlier forms remains part of the system's history, yet the current arrangement establishes a new identity, one that does not depend on what came before. Food chains regain a level of stability that supports sustained interaction across multiple levels. Energy flows from microscopic producers through a series of consumers, reaching predators that occupy the upper layers. These pathways, once fragmented, now function with greater consistency, allowing populations to maintain themselves over time. This stability does not imply uniformity. Variations persist across regions, influenced by local conditions such as temperature, depth, and nutrient availability. Each area develops its own balance, contributing to a global system that is both diverse and interconnected. Movement between these regions allows for exchange and adaptation, reinforcing the overall structure. Habitats within the ocean also reflect this emerging familiarity. Coral formations, open water zones, and deeper environments each support distinct communities, linked through the movement of organisms and the flow of energy. These habitats interact in ways that create a layered system, where processes at one level influence those at others. Behavioral patterns become more consistent as well. Migration routes, feeding strategies, and social interactions align with the established structure of the ecosystem. These patterns repeat over time, creating a sense of continuity that supports long-term stability. As these elements come together, the ocean takes on a form that can be recognized as a new normal. It is not a restoration of the ancient world, but a reassembled system built from the survivors and adaptations that followed earlier changes. Its structure reflects both continuity and transformation, shaped by the processes that have guided it through periods of disruption and recovery. Within this familiar yet distinct ocean, life continues to move, interact, and evolve, sustained by patterns that have settled into place over immense spans of time. What is absent begins to take on its own quiet presence, not through what can be seen, but through what no longer appears. The ocean continues to move with life, yet certain forms, once woven deeply into its structure, do not return. Their absence becomes part of the fabric of the new system, shaping it in ways that are not immediately visible. Entire groups that once occupied defined roles are gone without continuation. Their lineages end without leaving descendants to carry forward their specific adaptations. The patterns they created within the ocean, the ways they moved, fed, and interacted, do not reappear in altered forms. Instead, those patterns dissolve, leaving space for different arrangements to emerge. These losses extend beyond individual species. They include entire branches of evolutionary development, paths that had taken shape over millions of years. Each of these paths represented a sequence of changes that built upon one another, forming structures and behaviors that were unique to their time. With their disappearance, these sequences do not resume. The direction they followed remains incomplete, without continuation into later periods. The ocean that once supported these forms held combinations of life that no longer exist. Its ecosystems were shaped by interactions that depended on the presence of those organisms. Without them, the relationships that defined that earlier world cannot be reconstructed. The current system though stable and complex, reflects a different set of connections, one that does not replicate what has been lost. Fossil records preserve traces of these former inhabitants, offering glimpses into their forms and the environments they once occupied. These records show structures that have no direct equivalents in the present ocean, highlighting the distinct nature of that earlier world. The shapes, sizes, and arrangements of life captured in these remains point to a system that followed its own path, separate from what would later develop. The disappearance of these groups also influences how evolution proceeds. With certain pathways no longer available, new developments follow different directions. The organisms that persist and diversify do so within the context of what remains, building upon surviving traits rather than those that have vanished. This redirection shapes the long-term structure of life in the ocean. In this way, the ocean becomes a place where continuity and loss coexist. While many lineages continue and expand, others exist only in the record of what once was. Their absence does not create a void that is filled by identical forms, but rather contributes to the formation of a system that moves forward along a different trajectory. The uniqueness of the ancient ocean lies in these differences. It was not simply an earlier version of what exists now, but a distinct configuration of life, defined by combinations that have not been repeated. Its identity is preserved not through direct continuation, but through the contrast it provides to the present. As time progresses, the memory of that world becomes embedded in the structure of the ocean that follows. The systems that develop carry forward the influence of both what survived and what was lost, forming a balance that reflects the full scope of change. The ocean continues, shaped by processes that build and transform, yet it does so without returning to that earlier state. What existed before remains part of its history, but not part of its present, marking a boundary beyond which certain forms of life do not pass again. Recovery does not unfold as a return, but as a capacity to continue, shaped by processes that extend far beyond any single event. The ocean carries within it a tendency to rebuild, not by restoring what was, but by forming structures that can exist under the conditions that remain. Across long spans of time, life persists through adaptation. Organisms that endure do so not because they resist change, but because they adjust to it. Small variations accumulate, allowing populations to align with shifting environments. These adjustments are often subtle, yet over many generations they produce forms that are suited to the present rather than the past. This resilience is not uniform, nor does it guarantee survival for all. Some lineages continue while others end, and the balance between persistence and loss shapes the direction of recovery. The ocean does not preserve every form, but it maintains the processes that allow life to reorganize itself after disruption. Ecosystems begin to rebuild from these surviving elements. Each level of the system contributes to this process, from microscopic producers to larger consumers. As connections reestablish, energy flows through pathways that become more consistent over time. These pathways support interactions that grow in complexity, allowing the system to function with increasing stability. The rebuilding does not occur in isolation. Physical conditions, including temperature, circulation, and chemical balance, interact with biological processes to shape the outcome. Together, these factors create environments that support new configurations of life. The resulting systems differ from those that existed before, yet they fulfill similar roles within the broader structure of the ocean. Over extended periods, this process leads to the emergence of ecosystems that are both stable and adaptable. They are not fixed, but capable of adjusting to ongoing changes without collapsing. This balance between stability and flexibility defines the ocean's ability to persist through varying conditions. The lessons embedded within this process extend across deep time. They show that life does not depend on a single arrangement, but on the capacity to form new ones. Each period of disruption is followed by a phase of reorganization, where surviving elements combine in different ways to create systems that can endure. This continuity is not immediately visible, as it unfolds over timescales that exceed individual observation. Yet, it is present in the patterns that emerge, in the gradual increase of diversity, and in the reestablishment of connections that support life across multiple levels. The ocean, shaped by these processes, becomes a record of resilience. Its current form reflects both the changes it has undergone and the capacity it holds to adapt. The structures that define it are the result of countless adjustments, each contributing to a system that continues to evolve. Within this ongoing transformation, recovery is not a final state, but a continuous process. The ocean does not reach a point where change ceases. Instead, it maintains a balance that allows it to absorb variation and persist through time, guided by the same underlying capacity that has carried it through previous transitions. In certain movements of the present ocean, there are traces that do not belong entirely to this time, patterns carried forward through lineages that have persisted across immense spans. These traces are not immediately distinct, yet they reveal themselves in forms and behaviors that echo earlier worlds. Some of the organisms moving through today's waters descend from groups that endured through periods of disruption. Their structures retain elements shaped in distant ages, preserved not as exact replicas, but as continuations that have adapted while maintaining core features. The outlines of their bodies, the rhythms of their movement, and the roles they occupy within ecosystems carry a quiet continuity. Among these survivors are species whose ancestry extends far into the past, their presence linking the present ocean to environments that no longer exist. Their persistence reflects the ability of certain forms to remain viable across changing conditions, adjusting gradually while preserving the essential traits that define them. In this way, they serve as living connections between different phases of the ocean's history. This continuity is not limited to individual species. It extends to broader patterns within the ocean, including the ways in which life interacts and organizes itself. Some feeding strategies, movement patterns, and ecological relationships show similarities to those that existed long ago, shaped by the same underlying principles that govern life in water. These recurring patterns suggest that certain arrangements remain effective across different contexts, allowing them to persist even as other aspects change. The ocean carries these echoes without drawing attention to them. They are embedded within the ongoing activity of the system, present in the interactions that unfold each day. The movement of a fish through a current, the slow drift of organisms in deeper layers, and the coordinated behavior of groups all reflect processes that have been refined over time, shaped by both continuity and adaptation. At the same time, these surviving elements exist within a system that is distinctly modern. They interact with species and conditions that differ from those of earlier periods, forming new relationships that did not exist before. This combination of persistence and change creates a layered history where the past is present but integrated into a different framework. Fossil evidence provides a more direct view of these connections, showing how certain forms have changed while others have remained recognizable across long intervals. Comparisons between ancient and modern specimens reveal both continuity and divergence, highlighting the paths that have been maintained and those that have shifted. The presence of these ancient lineages influences how the ocean functions today. Their roles within ecosystems contribute to stability, as they occupy positions that have proven sustainable over extended periods. Their interactions with other species help shape the dynamics of the system, reinforcing patterns that support ongoing balance. In this way, the ocean becomes a place where time is layered rather than replaced. The present does not fully erase what came before, but incorporates elements of it into a new arrangement. Each surviving lineage carries a portion of that earlier world, not as a fixed memory, but as a living continuation. These echoes remain subtle, woven into the fabric of the ocean without standing apart from it. They do not recreate the ancient environment, yet they ensure that aspects of it persist within the ongoing flow of life. Through them, the ocean maintains a quiet connection to its past, carried forward in forms that continue to move, adapt, and endure. There is a quiet continuity in the way the ocean carries forward, not as a return to what once existed, but as a transformation shaped by everything it has passed through. The surface may appear familiar, filled with movement and life that seems steady and complete. Yet beneath that familiarity lies a history of change that has altered its structure in fundamental ways. The systems that define the ocean today are not direct extensions of those that came before. They are assembled from the fragments that remained, built through processes that unfolded over immense spans of time. Each layer of interaction, from the smallest organism to the largest predator, reflects a sequence of adjustments that have shaped the present into something distinct from the past. This transformation is evident in the balance that now exists. Food webs function with stability, currents follow established paths, and ecosystems support a wide range of life. These patterns create a sense of continuity, yet they are the result of reorganization rather than restoration. The ocean did not return to its earlier state, but formed a new arrangement that fulfills similar roles in a different way. Life within this system continues to persist, guided by the same underlying principles that have always shaped it. Adaptation allows organisms to respond to changing conditions, while interaction connects them within a broader network. These processes ensure that life endures, even as the specific forms it takes shift over time. Each phase of the ocean's history contributes to what exists now, not by remaining unchanged, but by influencing the direction of future development. The loss of certain forms and the survival of others have guided the paths that evolution has followed. What remains is a system that reflects both continuity and change, carrying forward the effects of events that occurred far in the past. This perspective reveals that the ocean is not a fixed entity, but a dynamic one, shaped by ongoing processes that extend across deep time. Its present form is only one moment within a longer sequence, defined by the accumulation of changes that have occurred over millions of years. The patterns observed today are part of this larger story, connected to earlier states that no longer exist. Beneath the surface, much of this history remains unseen. The movements of water, the interactions of organisms, and the structures of ecosystems all contain traces of what has come before. These elements do not display their origins openly, yet they are shaped by them, carrying forward influences that continue to define the system. In this way, the ocean becomes a record of transformation, where each moment reflects both what has been lost and what has been created. Its current state is not an endpoint, but a continuation of processes that will keep unfolding, shaping new arrangements over time. As this quiet story settles into place, it leaves behind a sense of how much remains hidden beneath the surface, how many layers of change exist beyond what can be directly observed. The ocean continues to move, carrying its history within it, shaping and reshaping itself in ways that extend beyond immediate perception. Share which part of this transformation stood out most to you, and continue exploring these quiet scientific stories that reveal how Earth's hidden systems have taken shape over time.